Good morning, guys. Today we're going to start working with radicals and rational exponents and seeing the relationship between them. We're all familiar with what radicals are, things like square roots, cube roots, fourth roots. Remember, a radical asks how many or what number raised to this exponent equals this value here on the inside. The exponent that we're trying to focus on is called the index, and the number we're trying to multiply to get up to is called the radicand. Rational exponents have a very specific relationship to radicals, and a rational exponent just means an exponent that's a fraction or a ratio of integers. So let's say we have this example, or this expression right here. Cube root of 16x to the sixth, and we want to simplify that down. Now, we can go through and break it down just like we usually do when we're simplifying radicals, where we'll factor it down and say 16 is 8 and 2, and then 8 is 4 and 2, and then 4 is 2 and 2. And so we keep going through, and a lot of y'all do this factor tree. I instead will write it as exponent. So 16 is 2 to the fourth. And then we have x to the sixth. Then we go through and we find all our powers of 3, because that's what cube root asks. What are the powers of 3? So if you don't recognize that 8 is a power of 3, you break it all the way down to here, and then you say, well, 2 to the fourth is 2 to the third times 2 to the first. X to the sixth is x to the third times x to the third. So we rewrite it as a bunch of powers of 3, because now we can answer the question, because we treat each factor as a separate radical. So what number cubed gives us 2 cubed? Well, 2 does. What number cubed gives us x cubed? X. What value cubed gives us x cubed? X. What number cubed gives us 2 to the first? Nothing does, because 2 to the first is smaller than 2 cubed, and 2 cubed is our smallest cube. So we go through just like we traditionally do with radicals. And so we see we pulled out 2x squared, and we're left with cube root of 2 to the first, because the 2 to the first, we didn't have any sets of 3 of. So that's one way we can go through and look at simplifying radicals down. Now another way is rational exponents, and that comes back to we're looking for sets of 3. So if I'm looking for all the sets of 3 that go into 6, or all the sets of 3 that go into 4, well, that's just like saying if I have 27 and how many sets of 3 are there, I would get that by taking 27 and dividing it by 3. So our rational exponents fit off this relationship that the nth root of a to the m is equivalent to a to the m over n. If I want to know how many sets of n are in this exponent, then I just take that exponent and divide it by n. These are equivalent expressions. So by comparison, we could have treated cube root of 16x to the sixth as 16x to the sixth, all of that to the 1/3 power, because we have the whole expression one time. Now we're going to go through and we're going to break them up here in a second and do the cube root of each individual piece. But that's one way we could look at this, is this expression to the 1/3 power. Now, do you always want to do this? You don't know. This one's pretty simple to do in this manner, but this just gives us another way to attack radicals that have very large exponents and or a very large index and things we're not comfortable working with. Square roots we're very good with, cube roots we're pretty comfortable with, but you get 4th, 5th, 6th, 12th power roots, anything of that nature. Putting them back into rational exponent form allows our exponent rules and our fraction arithmetic rules to kind of take over any of the simplifying and working with. And sometimes you're presented with it in this form and you need to recognize it as a radical. So if we were going to go through and use rational exponents as a technique to be able to simplify this down, I'm going to do the same thing. I'm still going to get it to be 2 to the fourth and x to the sixth. I'm going to factor my bases down, and then we just use exponent rules. Power to a power, right? And then we're going to distribute that and multiply them. So 2 to the 4/3 times x to the 6/3. Then we go through and let's evaluate, or change this form here and see how many sets of 3 do I have. Well, 4/3 is 1 1/3. 6/3 is 2. So we've already taken care of and found the x squared that we had out there with no other x's left over. Well, when I take 4/3 and make it 1 1/3, that's 2 to the first times 2 to the 1/3. All right, we're just separating that out because this is 1 plus 1/3. So that means I had two bases of 2 with an exponent of 1 and an exponent of 1/3. So as you can see, we've got the 2 and the x squared that we pulled out from this technique, and we're left with 2 to the 1/3, which our rational exponent definition there says is the cube root of 2 to the first, which is what we had right here. So 2x squared cube root of 2 to the first. So that's a way we can use rational exponents to help us simplify radicals down. It's not a mandatory, you have to use it. It's just like I said, another tool for us when we kind of get stumped or maybe have something we're not comfortable working with. We can get it into something we are, because radicals may seem kind of foreign and different for us, but exponents we've been working with for years. We're just going to change up whether now we're, instead of having whole number exponents or integer exponents, now we're going to have rational exponents. So, give me a second, I'll get a bunch of examples up here for us to play around and just manipulate things using these rational exponents and playing around with more radicals. So here we have 3 examples of different types of radical or rational exponent expressions. So let's try to simplify them down. So just like technique we did before, I'm going to start by just converting everything into a rational exponent. So I get 96x cubed to the 1/3 power. Cube root is 1/3 as an exponent. Now I'm going to go through and factor 96 down. So we know that's 32 and 3, and 32 is 2 to the 5th power. Okay, so we now have 90, nope. Not anymore. We now have 2 to the 5th power times 3 to the 1st power times x to the 3rd power, all to the 1/3 exponent. From there, let's just go through and use exponent properties for simplifying. So we're going to distribute, and that gives us 2 to the 5/3, 3 to the 1/3, x to the 3/3. And then just simplify each exponent. 2 to the 5/3 is improper, so that's 2 to the 2 2/3. 3 to the 1/3 is as simple as it'll go. X to the 3/3 is x to the first. And then we separate that one out. So that's 2 to the 2nd times 2 to the 2/3, 3 to the 1/3, x to the first. So our non-radical portion is going to be the 2 squared and the x to the first. So that's going to be 4x. The portion still underneath the radical is going to be anything with the exponent of 3. Now, if for some reason we had done that step where we made them into mixed numbers or reduced our fractions, and these did not have the same denominator on them, they'd have to be 2 separate radicals. So we want to keep them as the same denominator so we can put them underneath a single radical. So we're going to be left with cube root of 2 squared under the cube root, 3 to the 1st under the cube root. So we end up with the final answer, our final simplified expression of 4x times the cube root of 2 squared and 3, which is 12. So that's this expression right here. Take a second, pause the video, and go take a few minutes and try to simplify both of these down into a simplified radical expression, and I will hang out right here while y'all work on that. Okay, hopefully you've had a couple, or you were able to get answers for both of these. Let's check and see how you did. So we're going to start out. I'm going to convert it into a radical, convert it into a rational exponent. So I'm going to get 162 x to the 9th, y to the 6th, all to the 1/4 power. Fourth root is a 1/4 exponent. I'm going to go through, I'm going to factor 162. So 162, well, that's 2 and 81. And then 81 we should recognize as 3 to the 4th power. If you don't recognize as 3 to the 4th power, you can make it 9 and 9, which is 3 and 3 and 3 and 3. So 3 to the 4th power. So we have 2 to the 1st, 3 to the 4th, x to the 9th, y to the 6th, to the 1/4 power. Now your exponent rules take over. Power of a product, we get to distribute that exponent. So that's going to give us 2 to the 1/4, 3 to the 4/4, x to the 9/4, and y to the 6/4. Go through and reduce each of our exponents. 2 to the 1/4 is as simple as it'll go. 3 to the 4/4 is 1. X to the 9/4 is x to the 2 and 1/4. Y to the 6/4 is 1 1/2. So we get 3 to the 1st, x to the 2nd, y to the 1st. That's all of our whole number exponents. We're left with 2 to the 1/4, x to the 1/4, and y to the 1/2. So we're ready to put it back into radical form. So that's 3x squared y. Again, see how we don't have the same denominator for all of them? And the denominator is what dictates our index. So I'm going to rewrite this 1/2 as 2/4. That way I can put them all under a single radical. So we're going to get the 4th root of 2 to the 1st, x to the 1st, and y squared. So that is the simplified radical expression for 4th root of 162, x to 9th, y to the 6th. And so we're just using these rational exponents as a technique to be able to pull out all of our powers of 4 from that expression. The reason we're assuming all variables are positive just goes back to when you do even roots of negative numbers, you potentially run into imaginary. So just to kind of keep our focus on the simplifying process and the manipulations with the rational exponents and not have to focus so much on all the little definitions and statements that we would have to write out to say that this is going to give us a real number instead of potentially imaginary numbers. So the assume all variables are positive really doesn't affect how we work through it. It just makes our answer a little neater and cleaner. Let's look at number 3 right here. So we're going to start by doing the same thing as we did over here. They've just put it in rational exponent form for us. So we're going to factor out our base here, and 12 is just 4 times 3, which is 2 and 2. So we get 2 squared times 3 to the 1st, all raised to the 5/2. From there, let me get on the other side. Distribute your exponent. So we get 2 to the 10/2, 3 to the 5/2. Clean up your exponents. So that's 2 to the 5th, 3 to the 2 1/2. So we have 2 to the 5th, 3 to the 2nd, 3 to the 1/2. So 32 times 9, which is 288. And we're left with the square root of 3 to the 1st. Now, anytime you don't see a number on an index or see an index on a radical, it's understood to be square root. So we don't ever have to write a 2 there because that's implied when we don't see the radical there. So it is square root. So 1/2 power is square root. So that's 288 times square root of 3. So that's just simplifying single, radical, or rational exponent expressions. Give me a couple seconds and I'll get examples up here of ways to combine them, whether it be multiplication, division, addition, subtraction, all that good stuff. So like I said, give me a couple seconds, I'll get that stuff up here for you. So these next few examples we're going to go through, they can get pretty nasty. So if you want to try to pause and work these on your own ahead of time, just to see how you can do with them, you can go ahead and do that. But I'm just going to kind of go pretty briskly through them and not have y'all try to work any of these on your own, because they all have different little things that I'd like to talk about. But if you think you're up for the challenge, go ahead and pause at any point and see how you do on your own. So in this example right here, we have a single rational exponent expression. So we're just going to use our exponent rules. Before, though, I distribute that exponent, I want to try to factor down what's inside. So 8 I know is 2 cubed. 9 I know is 3 squared. I have two x's right here. Well, one of them has a negative exponent, so let's clean that up by flipping it to the denominator. Remember, negative exponents imply reciprocal. So x to the negative 1/3 in the numerator becomes x to the positive 1/3 in the denominator. And then we go through and I can just combine those together by getting a common denominator. So I end up with 2 to the 3rd over 3 squared x to the 1/2 and 1/3. Remember, you're going to multiply like bases. You're adding those exponents together. So you need to have a common denominator on those. So if they're both going to be denominator 6, it's going to be 3/6 and 2/6 gives us x to the 5/6, all raised to the 3/2. From there, it's just distribute your exponent. This is product of power of a quotient and power of a product. So we get to distribute that exponent to each factor. And then we just go through and see what we've got. So 2 to the 9/2 over 3 to the 6/2. 3/2 times 2, and x to the 15/12. Reduce each of your fractions. So we're going to get 2 to the 4 1/2. I'm just going to go ahead and separate it right there because we know it's 4 1/2, and we're going to separate in a second anyways. That's 3 cubed. We're going to get x to the 15 over 12, which is 5/4 if we divide by 3, so 1 1/4. Okay, so what we've got now is a radical still in the denominator of the fraction. Remember, we don't like radicals in the denominator of fractions, so we will often rationalize those denominators. Well, if it's a square root, we know we would multiply numerator and denominator by that square root because that's going to create a square for us. When you get larger radicals in here, you don't multiply it by itself. If I multiplied top and bottom by x to the 1/4, that wouldn't get rid of anything. That would just give me 2/4 down here. I still have that fraction exponent. So we do what I call completing the root. If I want to get rid of a 4th root from a denominator, I've got to have a 4th degree to do that. So if I have 1, excuse me, if I have 1/4 here, to complete it, I need a 3/4. So that's what I mean by completing the root. I've got x to the 1st, well, I need x cubed to give me 4 of them. So now that I've done that, let me do that in a different color so y'all can kind of follow that. This is something that I've put on to rationalize my denominator. So I'm tagging x to the 3/4 on. I'm multiplying numerator and denominator by x to the 3/4. And that's going to give me 2 to the 4th, 2 to the 1/2, x to the 3/4 in the numerator, 3 cubed, x to the 1st, and 1/4 plus 3/4 is 4/4, which is 1. Now we have no more radicals in the denominator. We're ready to put all this stuff together. So in my numerator, I've got 2 to the 4th, which is 16. Notice I can't put these together as a single radical because one has a 2 for denominator. It's a square root. The other one has a 4 for the denominator. It's the 4th root. So again, let's go through and make this 2/4. So I've got a common denominator between them. So I've got the 4th root of 2 squared and x cubed over 3 cubed, which is 27, and x to the first is x squared. And we'll go ahead and make this 2 squared into a 4. So this is our simplified version of this, our simplified radical version of this expression right here. So we took what was a square root and a cube root, a bunch of square root and cube root expressions, and actually turned it into a fourth root expression just by letting converting it all to rational exponents, and then just let your exponent properties kind of take charge there. Let's look at number 5 here, where we're multiplying. Well, just like before, when you multiply any numbers together, they've got to have the same exponent or the same base. So we've got to make sure these degrees or these indices right here have to be the same. So I'm going to start just like we did all this stuff. I'm just going to use rational exponents. Do you have to in this case? No. There are ways we could do it, just simplifying square roots, but we're practicing rational exponents, so I'm going to go to rational exponents. So I'm going to make this 5 times 2xy to the 6th to the 1/2 times 2x cubed y also to the 1/2. Because remember, if you don't see an index, it's an understood 2 because those are square roots. Let's distribute those exponents out. And that gives me 5 times 2 to the 1/2, x to the 1/2, y to the 6/2 times 2 to the 1/2, x to the 3/2, y to the 1/2. So we just distribute all those exponents out. Now we're going to put all of our like bases together. 5 is the only 5 on the board. I've got a 2 to the 1/2, a 2 to the first, another 2 to the 1/2. I've got an x to the 1/2, an x to the 3/2. So let's separate those a little bit. And I've got a y to the 6/2 and a y to the 1/2. So we put them all together. I've got 5, 1/2 plus 1 plus 1/2 is 2 to the 2nd. 1/2 plus 3/2 is 4/2, x to the 4/2. And that's y cubed. So that's y to the 3.5. So from there, we get 5, 4, x squared, y cubed, with a half a y, or y to the 1/2 left over, which should give us 20 x squared, y cubed, square root of y. Again, I can just use regular old simplifying radicals techniques, but we're practicing rational exponents, so we'll use rational exponents at the moment to get from here to here. Not just one way to do it, but this is just a new tool that we've got to be able to do it. Give me a couple seconds, I'll get some more examples of ways to combine radicals and rational exponent expressions together. So here's the last few examples. Let's say we want to add. We know when we multiply numbers, we have to have the exact same base or exponent on those values. When we add or subtract, remember they have to be like terms. You have to be counting the same thing, because remember that's all adding and subtracting is counting things. Right now I have 6 square roots of 18. I have 4 square roots of 8, and I have and I'm taking away 3 square roots of 72 from that. We're not talking the same language in all those cases. We're looking at 3 unique items there. So we need to get them to all be the same thing so we can count how many of this one particular item we have. If we have only one, we may have multiple items. It may be 3 unique items there. So before we can do any adding or subtracting, we've got to simplify each radical down and figure out what exactly it is we're adding, or subtracting, or counting. So just go through and we simplify the radicals like we've been doing. These are square roots, so they're pretty straightforward. 18 is 9 times 2. 8 is 4 times 2, and 72 is 36 times 2. So square root what you can. That's the square root of 3. That's the square root of 2. That's the square root, square root of that is 3. Square root of that is 4. Square root of that is 6. So we end up with 6 and 3, which is 18 square roots of 2, plus 4 and 2 is 8. square roots of 2 minus 3 and 6, which is 18 square roots of 2. So we're counting. I have 18 square root of 2's plus 8 square root of 2's, which gives me 26 square root of 2's, minus 18 square root of 2's, which takes me back to 8 square root of 2's. So to add and subtract radicals, we just have to simplify each radical down so that we're adding and subtracting the same radical. If we'd had different radicals there, we would combine the ones that are the same, and then the other ones would just tag along. We just have to keep record that they're there. So say for some reason I had a plus 2 square root of 5 on the end. When I got to this step right here, there were no more square root of 5, so I would just have plus 2 square root of 5 added on to my the end of what we could combine together. Now if we look at number 8 looks like it's pretty simple, except we notice there's a radical in the denominator, so it goes back to what we talked about before. Rationalizing the denominators, eliminating radicals, getting an integer for the denominator. Well, I have cube root of 4, and as I addressed earlier, I can't simply multiply top and bottom by cube root of 4, because that would give me cube root of 4 squared. Well, squareds don't cancel cubes. Cubes cancel cubes. So I want to complete this cube. Now, the best way to do it, to make my life easy, is to factor this first and figure out exactly how much more do I need. Yes, I could look at it as 4 to the first, and then say, well, we can cube root 4 squared, and that'll give me a 4 to the first 4 squared. But I don't have to go that far, because let me grab a new marker, because I can look at this as 2 squared. So I can rewrite this as 3 plus cube root of 4 over cube root of 2 squared. Now I don't need a 4 squared multiplied by top and bottom. I need a 2 to the first. Remember, to get rid of cubes, I need cubes. So I have 2 2's, I need 1 more. So from there I get, don't forget to distribute that, 3 cube root of 2 times cube root of both the same, so 4 times 2 is 8. So plus cube root of 8 over cube root of 2 cubed. And as we clean that up, cube root of 8 is 2 plus 3 cube root of 2. Remember, we just typically write radicals on the end of a sentence. And then cube root of 2 cubed is 2. So this ends up being our simplified expression, our rationalized expression. Okay, one last one that deals with rationalizing. 5 over 1 minus square root of 5. 5 over 1 minus square root of 5. So we don't have a single denominator or a single radical in denominator or a single term. We've got a binomial here. So remember, if we've got that, we treat it just like we do our imaginaries, and we use the conjugate to get rid of it. So it's just, you've done this before, just kind of rehashing it to make sure we're familiar with it. So we're going to do the conjugate of 1 minus square root of 5, which is 1 plus square root of 5. And you go through and do all the arithmetic, and you're going to get 5 plus 5 square root of 5. For the denominator, you're going to get 1 minus square root of 5 plus square root of 5 minus 5, which gives us square roots cancel. That was the whole point of using conjugate. So 5 plus 5 square root of 5 all over negative 4. And you can move negative to the numerator. Oh, not plus or minus, sorry. Force of habit on that. You can move the negative to the numerator if that makes you more comfortable. All over 4. Just divide both terms of the numerator by the negative 1. So that is how you would work if you had a square root as part of a binomial. You multiply numerator and denominator by the conjugate to get the rationalized denominator. Something I want you to think about before you come to class tomorrow. What if we had 5 over 1 minus the cube root of 5? How would we rationalize that denominator? Would it be the same way? Would we have to do something different because it's a cube root? So ponder on that and tell me when we get to class what you were able to come up with as a way to rationalize that denominator with the cube root instead of a square root. That's it for radicals and rational exponents, and I will see you in class tomorrow, guys.